We're in Chile's Atacama Desert, said to be the sunniest place on Earth. It's certainly one of the driest. But while it rarely rains here, the hills are often cloaked in fog that drifts in from warm oceans nearby.
So the question is, can I harvest it? Can I find some way of sucking that water out of the air?
Professor Gareth McKinley studies the rheology of complex fluids, or the science of how these fluids flow.
And really, we're surrounded by examples of things like that. So if you go into the kitchen, open the fridge door, anything like a mayonnaise or Vegemite or something like that is going to flow in a very strange way. It still flows like a liquid, but it may look like a solid to start with. You have to push on it to a certain speed before it'll actually start moving.
In collaboration with colleagues in Chile, his team used fluid mechanics to figure out an effective way to harvest fog in the Atacama Desert for much-needed water. It wasn't a new idea, but their approach was. The fishing nets and meshes commonly used to extract water from fog tend to be far from optimal. So Professor McKinley's team undertook extensive lab testing to design an optimised mesh consisting of stainless steel filaments about 3 times the thickness of a human hair. They also coated it in a special polymeric substance that helps trap the water droplets blown across the mesh in the air, but also allows them to drain down into the collector.
And you could literally collect drinkable water at the bottom of it. In fact, you really don't have to do any purification at all. It's naturally desalinated. You can turn it into just bottled water almost instantly.
Their desert deployment successfully yielded a few litres of drinking water per day from each square metre of mesh, which is roughly the daily requirement for a single farmer. But they think they can do even better with different configurations. It's the sort of challenge Professor McKinley thrives on. One of his career highlights was working alongside researchers from NASA to better understand the spinability of strong, stretchy materials such as spider silk.
So with a spider spinning its thread, it goes from a viscous liquid towards a soft solid that can hold an entire spider's weight. So we were really interested in measuring the properties or the stickiness or the stringiness of this. But of course, if you try and do that on Earth, then gravity dominates and your thread just sags to the ground.
He helped design special hardware known as a filament stretching rheometer that could be used to experiment with stretchable liquids on the International Space Station. Professor McKinley's other work is more down to earth. His insights on a range of complex liquids have been used in a variety of applications, from 3D printing to food manufacturing.
If I take the fat out of a product and try and replace it with something else that's vegan or vegetarian, then can I still make something that has the same taste? Or as what's used in the food industry, they call the mouthfeel. And mouthfeel is much more than taste. It's how does it feel in your mouth? Is it slippery? Is it slimy? Does it get stuck to the roof of my palate? And trying to match those kinds of properties is really what rheology is all about.
Professor McKinley first visited Australia as a student in 1985 and has worked closely with scientists here ever since, particularly at Monash University and the University of Melbourne. He says Australia has a strong reputation in rheology and calls becoming a corresponding member of the Australian Academy of Science a genuine honour.
There's very few corresponding members elected each year, and when I told my children this and they heard that David Attenborough was also a corresponding member, they were amazed. To me, if I can be mentioned in the same sentence as David Attenborough, then that's wonderful. But more importantly, it's really a great reflection of the collaboration and the science that I've been doing with colleagues in Australia for more than 25 years now.